Você compartilhou a tela, Lia? Você compartilhou a tela?
Sim.
Você ligou o microfone?
Acho que não.
Tá com o microfone aberto, sim, tá passando. Então, beleza.
É ali, eu acho.
Então, botaria do jeito que eu encosto no.
Vou usar esse?
Eu acho que sim, mas para cima você vai mexer, né?
Você pode colocar aqui, ó, na gola. Da outra vez que usou esse daqui, eu acho que foi melhor. Vou usar esse aqui.
Não, eu pode microfone que eu tenho que fazer com a mão.
Para ligar é só. Para ligar é só apertar o botão.
Tá. Não tá na hora ainda, né?
É meio que já passou da hora.
Não.
Vamos começar por isso. Okay, so good afternoon, everyone. We are back to the cycle of seminars of the astronomy department, and today we have Lia Doubrawa here with us today. She's an almost finishing PhD student here at the department, and every semester we invite a finishing PhD student to give a seminar, and Lia kindly accepted our invitation. And Lia is going to talk about the galaxy cluster detection and characterization in the S+ and miniJPAS surveys, and all questions can be asked after the talk. And also for those on YouTube and Google Meet, you can also ask questions after the talk. I just ask everybody on Google Meet to turn off your cameras and microphones. And yeah, you can go ahead.
Okay, so hi everyone. My name is Lia. I'm a PhD student here at IAG. And today I'm going to talk about my work, as Lia already talked to you. So I would like to thank the organizers for this invitation. I'm very happy to be here. Okay, so let's go. So this is a very nice picture that I found on the internet. That's my work. It's not about gravitational lensing, but we have here a cluster that is changing the light that comes from the galaxies behind of it and creating these beautiful arcs. So this cluster has become famous as these mining rings. But here we are interested in the galaxies that it's belonging to this cluster or to this kind of structure. Okay, so my presentation is divided in some major points. I will have a small introduction about galaxy clusters and the methods that I'm using in my work as my membership estimator. And some pretty results with simulations. And you will see that everything works fine here, but not as much in the real world. But it's okay, we are working on it. And in every one of these parts, yes. So I will have a small summary to mark as a starting point for the next subject. Okay, so our universe is composed of galaxies, groups, and clusters of galaxies, and these beautiful filaments, and also the low density regions that we call voids. And the formation of these theories are explained by the hierarchical formation theory, where the small-scale structures emerged earlier, giving rise to the larger ones. So in this process, the galaxy clusters have a privileged position as the largest gravitationally bound structures in the universe that have already had time to achieve some kind of dynamical equilibrium. So studying these structures along the time and of the universe, we can have the parameters that give rise to the universe as we saw today. So what is a galaxy cluster? As you may imagine, is a clustering of galaxies that have gas and a halo that is within this structure that is formed by dark matter. Right? So when we talk about some dozens of galaxies, we are talking about galaxy groups that are low mass structures. Low mass stands 13 solar masses and small radius, right? Because 1 megaparsec is not small, but comparing to the structures, this is a small thing. And when we're talking about hundreds of or thousands of galaxies, we have the galaxy clusters that are high masses, 10 to 14 or more, and larger radius that goes beyond 1 megaparsec. Okay, so as these galaxy clusters are bigger structure, they are also easier to find. But how that we do this? So with the development of the technology, we are obtaining even more data with these imaging surveys like S+ and JPAS. And to analyze all this data, we need computational techniques and computational power and techniques to do these analyses. And regarding these large scale structures, we use some codes that we call cluster finders that are based in different computational methodologies and different characteristics of what will be a cluster. There are several of them in the literature. Some of them are based on projected coordinates and photometric redshifts, while others are based on color filters, luminosity, or density profiles. So that's why, I thought that we use different methodologies to characterize a cluster. So here in my work, I'm using PZ-Wave, which is a density-based algorithm. It was developed by Anthony Gonzalez in 2014. And it is very interesting for the surveys like JPAS and S+, because it can use all the photometric information that comes from the PTS, and not only a single value for the redshifts. So the idea of this code is to divide the galaxies into different redshift beams, and then weight all of them by its PTF, creating this density mass. So using a difference of Gaussian scale, it can detect the galaxy clusters. So we use an inner scale. This means that it is the minimum value for these structures to have 400 kiloparsecs and 1.4 megaparsecs for the other scales. And well, after detecting all the structures in the density maps, the code merges all together and returns a detection catalog. Okay, but why this is important? So, as I mentioned before, we can use galaxy cluster to constrain the cosmological parameters. The idea here is one of the methods that we can do this is by counting the number of clusters with a given mass. So, but for doing this kind of method, we need precise masses for all the structures that we are measuring. And for restricting these masses, we can use gravitational lensing or X-ray analysis. But these methods can be very expensive depending on the number of the clusters that we are considering here. So for this, we use the mass observable relation, where we can relate something that are easily observed, like the richness or the brightness of these structures, and relate to mass. So this is what I'm doing. I'm looking for these relations to make an observable that is easy to find and relate it to the mass. So what we are thinking about a good minus proxy. So it must have a small intrinsic scatter, so we can have precise mass measurements. It has to be have a small dependence on the cluster dynamical state. So even if a cluster is merging with another structure, we can apply the same method without relying on other assumptions like equilibrium, and be easily accessed through observations. And we have several proxies that are already explored in the literature, like these ones, that have a small intrinsic scatter, like 0.2 to 0.3 in the log 10 scale. But we want to go even further and achieve these low results for what we have in our hands, that is the photometric information. And as all methods have a problem, here we have to deal with the errors in the photometric registers. When we have an error that is common of 0.01, we have a velocity that is proportional to 3,000 kilometers per second, which is 3 or 6 times larger than the cluster velocity dispersion. This means that we will probably be misclassifying galaxies as members and even creating false cluster detections because of this contamination. And how we can deal with that? With probabilistic memberships. Works like Castigliani, Bellingham, and Lopes have changed this formal view of it's a member or it's not by a membership probability. So this allows us to better describe the data and avoid this kind of contamination by galaxies that probably will be contaminated. Okay, so in the sense of these imaging and urban filter surveys, like S+ again and DPAS, the galaxy cluster detections is very the nice thing for the galaxy cluster detection because we can use the PDFs, right? So the methodologies for detecting this kind of structures is migrating from a color-based approach, where we deal with the galaxy red sequence, to others such as overdensities, like PZWave, that use the PDF to detect these structures. So think like that the cluster detection is already suffering these modifications in the codes. We have to think about how to characterize these structures using the photometric information. So for that, I have developed, as part of my PhD, this membership estimator that we call AMI, which I will show some steps of how it works. So with a cluster candidate and redshift and sky positions, we first select some galaxies within a fixed radius. This is a pure computational approach to have smaller costs for the repetition, because we do this several times. And then with galaxies that we have, we detect, we make a density profile with the galaxies and detect a break. Here with this break, we draw random redshift based on the PDFs. Then we calculate the cluster velocity dispersion using this random redshift that we estimated based on the PDFs. And we move the ones that are too far away from the cluster redshift by a 3-sigma clipping process. And then we run HDV scan, which is also a density-based algorithm that link together the points that are close to each other and mark the ones that are far away as a non-member. So by repeating these steps like 100 times, we can use all the PDFs, see how that galaxy influences the environment of the cluster. And finally, we have a membership probability as the number of times the galaxy is selected as a member in the HDV scan over the number of times that we run this code. I know that this is hard to understand, but I think that the next slides will be better. So here is a slide just to show how HDV scan works. So as I mentioned, is a density-based algorithm developed by Campello in 2013, where it looked for points one by one, they're close to each other. Then, by sorting this distance, they create these maps that meet the structures that are near each other. And finally, we have the segregation here and the points that they call as, I forgot that one members. Okay, so imagine that these blue points are galaxies, and the X here in the middle is the cluster center. So we apply the first cut, and we remove the galaxies that we know we are not using. Then we calculate the density profile and apply a cut. Here is in 500 kiloparsecs. So, okay, we just remove everything. And then we draw the random redshifts based on the PDS. So here we apply the 3 sigma clipping, remove the ones that are too far away from the cluster redshift, and run a scan. So we have these structures linked together, but they're close to each other. Then again, and again, and again. And after that, we will have a plot like this that shows the membership of the galaxies and in the distributed space here. So this is how UME works. Okay, so we have our method, we have everything that we need, so we go now test the results in simulations. As in simulations, we know already the cluster catalog and the galaxies that belong to each other, clusters, and the properties that we can use as mass proxies. So it's easier to make comparisons. Let's see if the code works. Okay, so we use a simulation produced by Pablo Araya that reproduced the first data release of S+. And from those, we take 919 galaxy groups and clusters that range from the redshift of 0.05 to 0.45, and masses that goes from the cluster masses to galaxy clusters with 10 to 14 and more. And then we apply UME and obtain some of the first results. Here we have the richness as a sum of the probabilities for each of the galaxies belonging to the cluster, and optical luminosity and total stellar mass. So here for optical luminosity, we have the absolute magnitude that is multiplied by its membership probability of each galaxy. And for the stellar mass, it's the same thing. The stellar mass of the galaxy multiplied by its probability. And here you can see that the colors are quite strange because they look like a Gaussian, and it should be more like this. And this happens because I'm applying a cut in membership that removes everything that has lower than 3 galaxy members. So because of the halo occupation model that has a natural scattering, it looks like that in the end of the cut. Okay, so I apply it, I have richness, and now I'm comparing with the results from the simulations. So how well are we recovering the true values? Here we have the true richness given by the mod, and this one is the richness that I'm calculating with UME. And here in richness means we can see that the median values are over the 1-to-1 line, which is great. And when we compare one by one and sum everything, we have a residual of near 0. So we are very happy with that. And now we can finally create these scaling relations. So here we have in black the curves that we achieve with the mod. So it will be the best value that we can obtain. And then the red ones are given by So, and here is the equation that I'm fitting. And what we are interested in most is the intrinsic scatter. So here you can see we have 0.18 for richness and 0.15 for optical luminosity, sorry. And well, the values are near each other for the simulations and for the ones that I'm taking, which is good. And they are also competitive with the literature because we are having like 0.2 or 0.3. So we have 0.18 and 0.50. And here you can see like the richness has the greatest implicit scatter. But because the moth already have this implicit scatter, like a structure with richness of 4, for example, can have masses of 13.2 to 14.2. So it's already very scattered here. And we can reproduce this, and so it's good. And another interesting result is with the total stellar mass. We have even a lower intrinsic scatter. So we would be interested to see how this works in the real data. And we think that is over optimistic because we already know the results when we give by the moth, right? And some intrinsic scatter may be introduced by the inference method in the real data. But even then, we have really nice results here. So we can test the code over small variations that we believe to happen in the real case detection. So for this, we take the study by Bernard et al. In 2022, where we run the piece wave algorithm over the same model that I'm using for this analysis. And they found a very small variation in the centers and also in the redshift values. So what we do is to take the center value and add 1, 2, and 3 sigmas and see how that the richness varies with these small offsets. And for the center variation, we can see that it doesn't affect too much our richness values. It's all within 0, which is nice. And these become to be worse when the centers are more far away than 250 kiloparsecs. So the variations start to be 5% in error. And this is a negative value because we are losing galaxies when we take the center too far away from the real center. And when we think the same thing for the redshift, so we have the galaxies, and then we take the point far away from the center, we lose a real important part from the cluster galaxies of the cluster, the galaxies that are close to the cluster center. So we lose a very important part of the PDF of these galaxies. So that's why the errors are quite large here in the 3C, because these errors are as large as the photometric error that we are considering for the simulation. Okay, so is summary part 1. So I showed to you the results that we have with the moths. So, and the algorithm that I have developed. And we have the scaling relations that are competitive with the literature. And we have a very robust code that it's okay when we have these small variations in a real case. And we have published it recently a paper about it. So if you want to see this. Okay, so real data. Now we're going to talk about the 4th internal data release of S+. And well, stay tuned because the 50 is already coming out. So S+, it has this beautiful filter system that is of 5 broadbands and 7 narrow ones. And this combination gives us very accurate redshift estimates. And it is located at Cerro at Chile with a telescope of 80 centimeters. Okay, so we have results for 5 of the 6 main areas of S+. We just leave S+D out because it is focused on the Milky Way disk, so we don't have interest in that. But we have more than 3,000 square degrees where we have clusters and groups detection. Okay, so we use the photometric redshifts and the PDFs that were obtained by a machine learning algorithm produced by A. If you have any interest on that, please talk to him because I don't know much about this. And the selecting criteria for our data. So we use the galaxy in size separation, and we take only the ones with 50% of being a galaxy. We remove everything with the sex factor that have this parameter of 2. We take all the galaxies with a magnitude lower than 21 in the R band, and we see the redshift range of 0 to 0.5. Okay, and as the pointings have some superpositions, we also want to remove these false when we have these points all together and increase the density of points, we are having a fake increasing in the density. So we want to remove that to actually find the cluster galaxies that we are intending to. So we take out everything that are close in 10 arcseconds and with a magnitude difference lower than 1. Okay, so as I mentioned, when we run PCWave, we end up with a catalog with an identification number, the sky positions, the redshift and redshift error. We have a signal to noise, and 3 other parameters that are based on the density mass. Like richness here is a measurement of the amplitude of this peak in the density mass. And radius is the radius of this structure, and rank is associated to signal to noise. So the greatest signal to noise, we have a rank 1. And we take all the clusters and groups that have a signal to noise larger than 4. Okay, so just some numbers of each of these areas. So here we have the number of galaxies for each of these areas and the number of clusters that we detected within the redshift range of 0.05 to 1.5. In the total, we have 150,000 groups and clusters. And here, just a comparison with the first data release, that a signal to noise greater than 3.3 and within this redshift range, and up with 4,500 galaxy clusters. So we have more galaxies, more clusters, but are they really reliable? Okay, so we tested with the simulations, with the fabulous model, and we found a completeness and a purity of this data of 9% and 80% purity when we apply a richness cut of 2.9. And if you're not convinced that this is a good thing, I compare with other catalogs in the same area. So here we have some optical catalogs, some based on X-rays, and we have very nice matching values for all of them. And when we talk about a match, we say that the cluster centers are separated with a value of 0.05 megaparsecs and a redshift difference of 0.05. And that's the matching value that I'm using for all these analyses. So here's some pretty results with UMI. So I have the cluster center marked by an X that was detected by PCWave, and UMI's galaxies that were selected within this radius. So we have, like in bluish colors, the most probable galaxy members, and going to the yellow ones that probably are just there. And the same thing for another one in stripe 82. Here is a galaxy cluster found in Hydra, and the redshift and richness and absoluteness values. Okay, so summary part 2. And okay, we run PCWave of the area. We have nice results of purity and completeness. We apply UMI for all the detections. And those things we still need to discuss if we apply or not, like future works. And if we will apply a region selection method for this catalog, because we may want to reduce the contamination and produce some calculations and mass calibration using weak lensing. This is something that we achieved in the miniJPAS, and we want to try in S+2. And we also have a work going on by Julia that is looking for merging clusters in the S plus data. And okay, we have also compared with the literature catalogs. And well, I have this data in my GitHub for now. I need to put S plus thoughts, but I need to talk with Gustav, I think. Sorry, I will do this in the nearby future. And as this is the internal data release, it's closed access, so you have to talk to me or to Claudia. Okay, so now in the last part of my talk, I'll be talking about results using the miniJPAS. Okay, so JPAS is a similar survey as S+. It uses 3 large bands for the photometry and 51 narrowband filters, which give us also very nice results for the redshifts. In theory, it must lead to us errors as small as 0.003. This means only 0.3% of the redshift estimate. But when we analyzed this data in miniJPAS, we found that these errors is around 0.12. So it's larger than the theory, but it's still very small, and we are very happy with this value. For S+, this value is something about 0.02. Okay, so JPAS is located at Jabalambre Observatory, which is in Spain, and it aims to observe about 8,000 square degrees of the continental sky. And but first, I will present to you the results in miniJPAS, which is a pathfinder for the larger survey, which has only 1 square degree, so it's a very small area. But it already serves to us as our members, our membership estimates, our cluster catalogs, and the cluster finders. We can do some tests and see what we are expecting for the larger survey. And recently, we have the first data release for JPAS, so we have a lot of work to do from now on. But right now, miniJPAS. So I run this wave over this area, and I found almost 600 groups and cluster candidates within the redshift range of 0.05 to 0.8. And I'm also using a signal-to-noise threshold of 4. And I also apply AMIN for these detections. And this is a quite large number for this small area. So we try to make the thing that I was talking about in the S+. And we've done that following a claim at all procedure. As we don't know exactly the distribution of clusters in this area, we compare our detections with random points distributed over the same area. And then we count how many points in this random catalog we have a richness greater than detected by this wave. And this will give us these curves. So when we apply a threshold of 90% of probability of being a real detection, we can remove the ones that are probably just overpositions of galaxies that are random. And by applying this method, we reduce our catalog for 221 cluster candidates. And this is the richness distribution here. And as you can see, we have 2 different cuts, one for redshift lower than 0.3 and other for the larger redshift. And this is done because we are trying to deal with the catalog incompleteness for the larger redshifts. So, but this doesn't mean that we are calling because we are calling as group regime and cluster regime, but we are not classifying these points as group or these as cluster. We are just giving like more but we will be giving like considering the cluster or the group optical luminosity, we will have wider cuts or shallower cuts that will give a more, sorry, I forgot how to say that. But okay, so we can characterize this sample better with a smaller brightness cut. Something here with a brighter cut. Okay, so we have compared this catalog with X-ray catalog from same area of miniJPAS. And by reanalyzing the fields, we found 37 matches here, where 20 of them are new detections. And here in this plot, you can see the distribution of masses and redshifts. The circles are the Popche catalog by Efania 5, 2013. And the stars are the corresponding clusters found by these waves that have an emission in X-rays. And here I'm highlighting this structure at redshift 0.75 that has a mass as low as 4, 10 to 13 solar masses. So it's a small group at high redshift. This means that we have nice data and that our methods are good, that are working, and we are very excited to see what we will find in the new data release. The masses come from scaling relation from Lia Doubrawa, 2010, where she used this weak lensing calibration to calculate the mass. That is something that we want to do in S+, and we done that. Oh, I just eating spiders. But we done that for miniJPAS. So this was a work done by Dr. Andrea Vitorelli, that was a student here at IAG. And he was able to constrain the mass in the miniJPAS using the weak gravitational lensing technique. And this is quite amazing because we have a small area, and even so we could apply the technique and have some results of masses. And you can see here 10 to 13 and 10 to 14 solar masses. That is the same range that we are achieving with this catalog in the X-rays. And for that, he used the CFHT length data and the richness estimates given by UME and another catalog in the same area. Okay, so just coming back for this plot. So we've done some scaling relations using this data from here, these mass estimates. And as you can see, they are not as pretty as the one obtained with simulations. But this is something that we can do, but we need more data to make this look better. Okay, so as I mentioned before, we have other cluster finders working in the same area where we can compare the results with phase wave, AMICO, and VT. AMICO is a cluster finder that uses those relations with the density profile and the luminosity profile. And VT is a pure geometrical code here, where it calculates the distance between the galaxies and where it finds something that looks like a cluster marks a cluster. Okay, so when we do this matching procedure, again, the same values that we were using before, we have 43 common clusters between all the catalogs. And what we are seeing here is the center distance between these 43 clusters. And 2 by 2, like phase wave, VT, AMICO phase wave, VT, and AMICO. And this is important because when we do the analysis of weak lensing, we need to consider this sampling. So the idea here was to find some trends, and we can see like something like this. But it wasn't enough to really constrain and add a function that could help us in the weak lensing analysis. But we have an overall difference between the center of 100 kiloparsecs. And when we compare the distance between the redshifts of these 43 clusters, we have very small values. So, okay, we at least can constrain well the redshift. Okay, and as last thing that I would like to say is the significance of the catalog. So the idea here is to compare our detection catalog with a catalog of massive galaxies. So studies by Gonzalez et al. Created a simulation that relates the halo mass with the mass of the BCG, with the stellar mass of the BCG. So as we have the stellar masses, when we apply a cut of 2, 10 to 11 stellar masses in the stellar mass, we think that we are taking the clusters with masses that goes within 10 to 13 to 10 to 14 solar masses. That is the range that we are working here. Okay, so here the matching procedure is for 1 megaparsec, not 0.5. And we search for the fraction of isolated galaxies, so the ones that we are missing in our catalogs, considering that they reside in a halo. So these have 2 redshift ranges, and for the small redshifts, we have a nice coverage of all the galaxies. But when we go to higher redshifts, we lost a lot of it, taking only 40% of these galaxies are clustered in our catalogs. And this wave has a really interesting result for you, but the catalog is larger, so we have more protections, and this is something that, okay, so happens. And this wave is also made to work at high redshift, so maybe this is why we have better coverage with this wave. And when we take only the galaxies, the fraction of isolated galaxies lower than 0.2, take the clusters that are separated in this redshift range, and estimate the minimum halo mass that we are detecting in the redshift range. So that goes from 5, 10 to 13 solar masses, also 1.10. So everything is in order. And the summary part 3, and this is the last one. So we have our code working on miniJPAS. We have the richness selection method. We have the overlapping area with X-rays, and we have 20 new detections, which is very nice. And the matching between the cluster finders will be some common identifications with small sets. So yeah, we are good. And that's it. Thank you very much for your attention.
Thank you, Lia. We have time for some questions. So does everybody here in the auditorium have a question? So.
Lia, muito obrigada pela sua seminário. Oh, sorry. Thank you very much for your talk. It was really nice. And I appreciate it was in English. That's good, a good practice. First, I would like to say that IDR4 will become DR4 very soon, like within 1 month. So it will be open to everybody. But more than that, I'd like to say that anybody that wants to become a member doesn't even need to talk to Lia or me, can just write to West Plus at IAG-USP PR and say that you want to be a member, and then you can have access to any day. You can play with the data if you like. Okay, so this is important to advertise in an audience like this. Lia, you have made a lot of tests with your sample from miniJPAS. It's a small area, it's easy, there are lots of catalogs from this area, but I was worried that you didn't check so much the catalogs from S+, for example, with X-ray detected or any other search that was done to see how many that you recovered that are real ones, plus what's the best redshift range for your detections. I think this is really important. I don't know if you have done anything in the latest times, because I know you when I talked to you maybe 6 months ago, you have not had time, but maybe now you have had other experiences. Okay.
Okay, thank you very much, Claudia. So I didn't have time again to look more closely for this issue, but I have compared data with some headlogs that we have for SARS-CoV-2. And here we have the optical and also the X-rays, and also I think that's Lia Doubrawa. And we have the matching values for this catalog. So we are at least in completeness very well.
Can you say a bit
What's the difference in kiloparsecs between the centers?
Oh yes, is 0.5 megaparsecs and 0.05 for the redshift difference.
0.5 megaparsecs, so half a megaparsec,
Yes.
500 kiloparsecs, and that's very much. It's a lot, right? Do you know that if it is the same? That is the same system? Did you check any of them?
Not yet. But
Yes.
this is something that we are using in all our matching systems, even for the mocks and even for
You
the
use this value,
We
okay,
use
so,
this value.
okay. And how about the ones that were found by Stephanie? Did you find the same?
Yes.
Okay,
And they are
good.
there.
So, yeah. Sanity check. Okay, thank you, very nice,
Thank you.
thank you.
Thank you. Does anybody here in the auditorium also have a question?
Thank you for your talk here. Just a small doubt. It wasn't clear for me, like when you're choosing your first artwork and how to choose your galaxies. You said you were looking for the ones that are close, but you are looking like close in angular distance or in just angular distance.
Yes, they are all project. They are all projected in space. So we look at galaxies that are close in the space.
All right. Okay. Thank you.
Any more questions in the auditorium? Oh, okay.
Thank you here for the talk. Here about this comparison between the distances from X-rays and the optical. These X-rays are the center of the gas of the cluster, or X-rays from the galaxies themselves.
I think this is from the gas.
Is like gravitational lenses, is it possible to establish some center for this some of these galaxies present in your sample? Maybe
Yeah, not exactly the galaxies, but we can make the mass maps, and we can find the center in this mass distribution.
it's interesting to see us.
Thank you.
Thank you. I do have a question myself. Yeah, in your algorithm, like in the beginning, when you apply the HDD scan, from what I understand, like you resample the photometric redshifts from the ETFs, like in each like iteration of your like your code. So like when you do this process, what should happen with like the HDD scan is to generate a different cluster, different from the first one. Like for one sample of PDFs should generate a different cluster from the second sample. So like for you to do this, like do you fix the number of clusters that you want to find, like this to one, in order to like fix the cluster to guarantee that you're not like your galaxy is going to two different clusters. So that will be the most.
Okay, so we are using a very small radius, and the cluster center is always fixed. So we only change the galaxies there in the place, right? So we don't have this worry of a galaxy belonging to another, because we are using a very small radius.
Okay. Okay, and another question is like when you're comparing two simulations, like you compare the scaling relation between the mass of the clusters that you derive, like from like using your code, and then from simulations, like with the stellar mass, like that you find in the simulations. But like, how does that work? Because from what I understand, like in your code, you should be like it seems to me that you're being very conservative in like selecting your galaxies that belong to the cluster. So like, how come like your applying your code that generates the same like luminosity and stellar mass, given that you should be discarding a bunch of galaxies like in the outskirts of the cluster in comparison to the simulation. Or like you apply a similar cut to the simulation, then you match.
Yes, we apply the same cut. So we are comparing orange with orange not. Everything is inside the same characteristic radius.
Okay. So everything is inside like the same radius, and then you
Yes.
apply like the same ratio. Do we have any questions like movement? Relative, please you can open.
Hi, Lia. Congratulations for your talk. I have a curiosity. I noticed that you have considered only objects with redshifts above 0.05 in PZ wave. Is there any reason for that or what?
You mean for S plus, right? For
Yes.
is lower than 0.45. Yes, so we have the completeness of the catalog. So they are complete for this redshift range. So we find it.
But in principle, could it be applied to lower redshifts? For example, the Hydra cluster itself is at redshift 0.01. It would be maybe interesting to see whether the code is able to recover the groups and the other clusters like Antlia that are in the region. All of them with redshift smaller than 0.05. That's why I'm asking the question.
Yes, I understood now. So PZ wave was made for work at high redshifts. So when we apply to these regions that are very low redshift, it cannot like work properly because our BPDS will cover almost all the area. So it can't actually precisely find the center of the cluster. But of course, if we have a redshift and these high conditions, we can run AMI without problems.
Okay, thank you. We can talk about it later.
Okay.
I think Professor Bacci also has a question. Bacci, you can go ahead.
Okay. Hi, Lia. I have a question regarding the mass distribution that you probe from your sample. This because you are in this very interesting redshift range where from where it comes most of the diffuse high energy emission in the universe, gamma ray emission, neutrino emission, and this in turn can probe cosmic intergalactic magnetic fields very nicely, and also constraints for dark matter. So knowing, the distribution, the mass distribution of this range, it's of clusters and group of galaxies in this range is a very nice constraint that can be imposed from observation. So what is the typical range that you get in this region? I know that is around 10 to 13, but what is, the range, the extent? Can you say something about this?
Yes, thank you, Betsy, for your question. So at least here for miniJPAS, we are going from 10 to 13 to 1 or 2, 10 to 14 solar masses. And well, at least for this sample, this comparison with Ephania firework, we are constrained within this range, but and we go for low masses here at high redshifts.
Right. Mm-hmm. Yeah, that's interesting. Thanks.
Thank you.
Okay, is there any other question here in the auditorium? If not, let's thank Lia again. And we'll see each other in the next seminar. Which is next year.
It's rápido, mas sim.
Vou fechar aqui.
Yes.